So I will be talking about stars lensed by the supermassive black hole in the center of our galaxy. And I've done this work with Przemek Mróz, currently in Warsaw and at that point at Caltech. So this is the basic setup of what I will be talking about, gravitational lensing. The only difference is that my lens here would be supermassive black hole, and my source, instead of a galaxy depicted here, will be a single star. So we have a lot of examples of galaxy-galaxy lenses. One example shown here, which are quite good for many purposes, including measuring the masses um, and some cosmological applications. But in this case, both the lens and the background source are not point-like, they are quite complex and non-uniform. So it may be a bit difficult to do everything what lensing can provide. So if we now consider a star-star lensing, then a star is lensed by a star. We have a lot of example of so-called microlensing. So an event that a star is being brightened very characteristically because of something else coming it for a short period of time. And we do not usually resolve the images into two or more, but we just see this brightening as the lens is coming close to the image of the background source. So that resolving of the lensed images was done only for one star-star lensing. So only one star lensed by another star was resolved into two images, which is shown here. So yeah, it's just one case. It's just difficult because the scales, the spatial scales here are so small that it's just not easy to do. And this is actually important because unlike galaxy-galaxy lensing, here we would have point-like lens and point-like source, and that's very simple geometry, so very easy to deal with, and that would be it would be possible with that to test the general relativity and do some cosmological analysis. So, but that's not possible because there's only one such configuration detected so far. So what I will focus on here is another scenario of point-like lens and point-like source, which will be the supermassive black hole in the center of our galaxy. So 1 arcsecond vicinity of supermassive black hole is shown here. We have the black hole position shown by cross and a lot of stars around them. Unfortunately, the Einstein radius, so the scale of lensing, is for these stars is very small. It's 5 milliarcseconds, so it's not possible to resolve, or very difficult to resolve currently. And that's because when we look at orbits of these stars around the supermassive black hole, they don't really come very far behind the supermassive black hole. So the Einstein radius is, of course, very small. So another idea would be, instead of looking at stars which orbit supermassive black hole, to look for stars which are behind the supermassive black hole, very far in the background, because for them, if they're sufficiently far away, the Einstein radius is of the order of arcseconds. So that's very easy to detect, very easy to resolve, and that can be studied. So basically my question here, which I want to answer, is can we look for these background stars with the upcoming and current facilities? So what we did is basically to calculate how many of these stars we expect for a given setup, telescope and instrumentation. So we considered a range of distances from us to these stars. So we consider distance up to 16 kiloparsec from the supermassive black hole. So we basically assume that the Milky Way ends at 16 kiloparsec. And that gives us the calculations of the Einstein radius and also the dust-corrected limiting magnitude for these stars. Because of course, further the star is, more difficult to detect because of the distance and dust. And then we also integrated over angular separation between the supermassive black hole and the star, and that's depicted here. So the observer is at the top of the cone. Supermassive black hole is somewhere on the central line here. And now we consider stars which are at a given distance from the observer, and also at a given angular separation from the black hole. So the angular separation from the black hole gives you the amplification of the secondary image, because obviously in order to do this, you need to detect both the primary lensing image, but also the secondary lensing image, because if you just detect the primary, then you don't know that the stars is actually lensed. So we considered only secondary image amplification. And also this angular separation gives you the volume, which is probe. So then we basically integrated over all distances, all angular separations, and then integrated a luminosity function of stars in the disk and the bulge in order to, and kept only those stars which are bright enough to be detected by a given telescope. So we basically ran all of this, and for given setup, we calculated how many stars can be detected if they are lensed, meaning that we detect both the secondary and primary lensing image. For dust attenuation, we assumed 3 different options. So very optimistic case here. So this is dust attenuation as a function of distance from the galactic center. The very optimistic case is that there is basically no dust behind the supermassive black hole. So it's very optimistic and not realistic. That would be the blue line. And then other assumptions are that the attenuation grows linearly with distance, or that the amount of dust falls off exponentially from the supermassive black hole. So that's actually the most realistic assumption, the black line. So these are the results. So basically for many different telescopes, so ELT, TMT, GMT, James Webb, and existing telescopes, we calculated numbers of lensed stars which we can detect on the y-axis as a function of distance from the supermassive black hole. And different colors means different attenuation curve, attenuation assumptions. So the black line is the most realistic ones. And then the dotted lines are for the stars in the bulge, and the solid lines are for the stars in the disk. So we see that these new upcoming telescopes should be able to see of the order of hundreds of lensed stars. So that's a very good news, that we will be able to study them. And consistently with the currently available data, the current telescopes should not be able to see any lensed stars, because the expected number of stars is lensed stars is below 0.1. So here the first key characteristic of observations which are needed for that is of course sensitivity, because the number of lensed stars grows when your limiting magnitude gets better and better. In order to get around 10 such lensed stars, you need at least 24 limiting magnitude. If you want more, a few tens, then probably 27 or 28. So that's the sensitivity. With that sensitivity, which will be available, the telescopes will be able to see around 100 lensed stars, as I said. However, for James Webb, there is a complication here, because in these calculations, we do not include confusion. And James Webb will have worse resolutions than the other telescopes considered here. So it will be actually heavily confused by stars which are orbiting the supermassive black hole. So with James Webb, it will be difficult probably to see that. And well, at least 24 magnitude is needed. And the method here is quite simple. We just look for 2 stars which are exactly on the same side of the other side of the supermassive black hole. They have the same spectra and fluxes which satisfy the lensing equation. And we also checked if it will actually be possible to see these characteristic elongated arcs as we see for galaxy-galaxy lensing. And that turns out not to be possible, because to see a star stretched, we would need a stretch for at least a factor of 1,000, because stars are small. And that reduced the numbers by a factor of 1,000,000. So all the numbers shown before would be below 1. So we do not expect even a single star to be stretched in an arc. But what we consider possible is the rotation of the lensing images, because the proper motions are several milliarc seconds per year. So the Einstein crossing time would be 100 years. So that is the time scale for a full rotation of the lensing images. So with a decade-long monitoring, it's actually possible to detect the motions of these lensing images.
You're out of time, so
yep,
yeah.
I finish here with showing the conclusions. Thank you.
Sorry. All right. Thank you for a very nice talk. Are there any questions from Kat? Okay, so I can see a question from Ralph Steven Morgan. He asks, what are the derived physical parameters of a lens star event from the black hole?
Once more.
What are the derived physical parameters of a lens star event from the black hole? So I guess what information you get using the lensing technique.
Yeah, well, about the star, probably not that much. You basically can measure the black hole mass. That's the first thing you can easily do. And then if you have a larger sample, you can test general relativity. That's the best thing you can do with that, because that would be the very independent test and kind of geometrical test of general relativity.
Right, okay, cool. I have a question about the confusion you mentioned because of JWST slightly worse resolution. So is there any way that you can model this and work out the statistical likelihood of whether a star that you are looking at is from the galactic center or behind it? Or is it like how much will this affect your sample? Because like if you have only a few that you're looking at with JWST, I can imagine it's not as important and you just rely on the ELT, TMT, GMT data. But have you considered doing that modeling? Is it worth doing? I was just wondering.
Yeah, well, we did very simple calculations. So we just take the numbers of stars currently visible close to the galactic center, and we kind of extrapolated that down to the limiting magnitude we were considering and asked the question, how many stars would land in a single beam? And for James Webb, that was like 10 stars per beam. So yeah, well, if it's a very bright lens star, then yes, James Webb would see that. But if it's one of the faintest we are considering here, which are actually needed because they are more numerous, then James Webb would struggle to see them. That's our, but this is very simple calculation. We just extrapolate the unknown luminosity function to the faintest magnitudes.